Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 2nd, 2025, just yesterday. This paper introduces a training-free method that allows a small 3 billion parameter model to beat Gemini by 16% on average across a range of tasks. The paper is titled MARVIS, Modality Adaptive Reasoning over Visualizations. And the core idea is really clever, using visual reasoning as a kind of universal translator for different data types. Essentially, it transforms non-visual data like audio or tables into special images that a vision language model can then interpret. Also, the authors shared their official implementation on GitHub, and it's quite comprehensive. You'll find the full code, of course, but also a getting started notebook and plenty of examples. They have quick start guides for using MARVIS on tabular data, audio, and vision, which is a great way to dive in. Okay, so this first figure really visualizes the core claim. It's a radar chart showing MARVIS's performance across different data types, like vision, audio, and tabular data. The solid colored lines represent the MARVIS 3B model, and it achieves these results using only in-context learning. In-context learning is the ability of a model to learn a task from examples in its prompt, without any retraining. You can see the MARVIS line consistently stays near the outer edge, close to the specialized models, and it dramatically outperforms other general approaches. Alright, so how does MARVIS actually achieve this versatility? This diagram breaks down its elegant four-stage pipeline. It starts with raw data, which is fed into a specialist model to create an embedding. An embedding is a dense numerical representation, like a digital fingerprint, that captures the data's key features. Then, a technique called dimensionality reduction, using a method like t-SNE, takes that complex embedding and plots it as a 2D image. Finally, that visualization is shown to a vision language model, which reasons over the image to make its prediction. Moving to the results, this table then details how well that pipeline actually works across those different data types. It compares MARVIS against both specialized models, which are experts in one domain, and other general foundation models like Gemini. You can see that MARVIS is incredibly competitive with the specialists, often coming within just a couple of percentage points. But when you compare it to other general models, the improvement is huge. On the open MLCC 18 tabular data, for instance, MARVIS scores 84.5% accuracy, blowing past the next best foundation model at just 50.1%. Building on that pipeline, this next chart explores which visualization strategy actually works best. Remember, a key step is turning data into a 2D image for the vision language model. This chart compares many different ways of creating that image, plotting their mean accuracy. The top performers are what are called perturbation-based approaches. A perturbation-based approach is where they slightly alter the data points to see how stable the visualization is, which gives the model a sense of uncertainty. This result suggests that showing the model not just the data but also its stability really improves reasoning. So to really put its performance to the test, the authors use what's called a critical difference diagram. This chart statistically ranks different models, where a lower rank is better. You can see MARVIS is ranked very competitively, right alongside strong traditional methods like random forest and catboost. The black bars connect models whose performance differences are not statistically significant. What's really striking is that MARVIS is in a completely different statistical group from other LLM approaches like Tab LLM Gemini, meaning it significantly outperforms them on this tabular data benchmark. So digging deeper into why MARVIS performs so well, this table analyzes the quality of the model's reasoning. It compares features of the text output when the model is correct versus when it is incorrect. You can see that correct predictions have longer responses, more mentions of color, and more explicit distance reasoning. This suggests a deeper spatial analysis. In contrast, incorrect answers rely more on simple heuristics, which are like mental shortcuts. For example, it uses the closest or majority rule more often when it's wrong. This finding really shows the model engages in more thorough reasoning when the visualization supports it. So, in conclusion, the MARVIS pipeline offers a really powerful and training-free way to make vision language models versatile. By turning complex data, like tabular or audio, into visualizations, it allows even small models to reason about them with surprising accuracy. We saw that it's not just guessing. the quality of its reasoning actually improves when it gets the right answer. This approach effectively creates a universal interface for foundation models, tackling challenges in flexibility, privacy, and domain-specific training. That's all for this week's AI Research Roundup. Thanks for tuning in.